Section 3.2 is addition and subtraction of whole numbers. To start with, just looking at a definition, we're going to let A and B be two disjoint finite sets. If the number of items in set A is A and the number of items in set B is B, then adding A and B together is the same thing as counting the number of items in A union B. Those lowercase a and b are called the addends, and A plus B is called the sum. Okay, so there's one part of this that we could sort of just gloss over and I could not address it, but I think it's valuable to recognize that when people are creating and stating definitions, that the details in the definitions really are important. And in particular, the detail that I want to focus on is the word disjoint here. So take a look at example 1. It says it wants us to give an example to show why in the definition A and B must be disjoint. Why does that actually have to be the case? So in particular, how do we do that? Well, we create something that's not disjoint and show that it doesn't actually work with our definition. So we're going to create A and B. And what does the word disjoint mean? Disconnected. They're absolutely disconnected. So if you think in terms of our Venn diagrams, they're two separate circles that don't have the overlap, okay? So we're going to create something that's not disjoint, which means they are connected and they do have an overlap. And we're just going to create a numerical or a letter example or something like that. So give me some examples of things, letters or numbers that you would like to put in set A. 1, 2, 3. All right. What do we want B to be?
1.
Okay. And how about we throw something extra in? Can we throw something extra in? 5. You don't have to have extra, but I don't want you to think that one of them has to be sort of inside of the other one to make this work either. So let's count this. How many items are in set A? 3. How many items are in set B? 3. And if I were to count, or if I were to add these together, right, this is the little a in my definition, this is the little b in my definition, and I did A plus B, what would I get? I get 6, yeah. Come back over here to A and B. What is A union B?
1, 2, 3.
1, 2, 3, 5. And what is the number of items in this union? 4. And you can see that these two things are not equal. If they'd been disjoint, they didn't have anything overlapping like that, they would be equal. Does that make sense? And the reason is because, of course, when you count them the first way we counted, the 1 and the 3 were counted twice. Do you see that? We counted it when we counted set A, and we counted it when we counted set B, so we ended up with counting 2 extra, i.e. the overlap. All right, we're going to focus in Chapter 3 on our 4 basic operations for whole numbers, which is addition, subtraction, multiplication, and division. Today's focus is addition. Monday will be subtraction, and then we'll move on into the other sections of the chapter after that. And what we're going to start with on addition is models for addition. So we have, I think it's 3 models, or is it 2? It's 2 models for addition. I think it's 3 models for subtraction. 2 models for addition. One is called the set model. So the set model is typically used for whole objects. So for example, when we talk about a crayon, even if it's like, you know, a smushed down one because it's been used, we still act like it's the whole thing. You know what I'm saying? Like we talk about a whole object being a crayon. So this is why this definition or this example is used here. But you would count whole people, right? Don't count half of people's. That's a bad idea. We would count whole desks. Half a desk is rather useless. So these are whole object things with set models. So here's our example. Liz has 3 blue crayons and 2 red crayons. If she combines all of the crayons, how many does she have? And this is a really nice example when you're working with young children because you can actually draw the picture really quickly, right? So here's my 3 blue crayons. And then I have 2 red crayons. Right? And you wouldn't even draw this if you were working with kids. You'd actually have crayons sitting there, right? And they would move them over and they'd count them one by one. And when they count the total, they end up with 5. So this is 3 plus 2 equals 5 crayons. And these objects are whole objects. Okay? So you might be thinking, okay, well, aren't most of the objects you deal with whole objects? And the answer is no, they aren't all whole objects. A lot of them at the earliest ages we talk with kids about are. However, there are things that aren't whole objects too. So I've got an example here that maybe doesn't really work for my 5-year-old, but I'll give you an example here in a minute that maybe would. The second model is called a number line or a measurement model, and it's typically used for objects that can be partitioned, broken into pieces. So we're not breaking them into pieces, we're still using whole numbers, but it's an object that makes sense when you talk about half of it. For example, Joe has 4 feet of wood and 3 feet of aluminum. How many feet of building material does Joe have? So while I'm not dealing with, 3.5 feet of something, we recognize that that's a real thing, right? I could really talk about 3.5 feet and it would make sense, but if I talked about 3.5 humans, that no longer makes sense, right? That's the difference here. And when you're looking at this particular one, it actually allows itself to be measured along a number line. So if you start at 0 on your number line and you sort of lay his particular objects end to end. So we have, what was it first? 4 feet of wood. So we have 1, 2, 3, 4 feet of wood. And in terms of a number line, right, we're counting along the number line. Here's 1, 2, 3, and 4. And then we're supposed to have 3 feet of aluminum. I think I need to move my diagram a little bit to the left to have enough space. So after 4 would be 5, and then 6, and then we have 7. So we're counting from a number line perspective, right? So again, I said, aluminum and wood and these things won't make a lot of sense to my child, but if I talk about cookies, it would. I don't know about you, but when I work with little kids, a half a cookie is not the same as a whole cookie. Are you with me? So if we were counting cookies, they'd have to actually be a cookie, meaning the whole thing, to count it that way, and we could do the same sort of thing. So that would be an object where you could divide it into pieces, and it would actually make sense for a child. All right, a phrase that we use frequently are the phrases less than or more than. So what do we mean when we say less than? For any whole numbers, A and B, A is less than B, written with the less than symbol. If and only if there exists a natural number K, such that A plus K equals B. And you guys know this to be true. You may not have thought about it that way, but the reason that 2 is less than 5 is because there is a number I can write here that makes this statement true. Right? It's the number 3. 2 plus 3 is 5. If there's not the ability to put that number in there, in this case the 3, then this is not a less than statement. Okay, and it's got to be a whole number I'm putting in there too to make it work. So thinking about the way that this is phrased, what we're going to do is we're going to give a similar definition of less than, but we're going to do it using subtraction instead of addition. So think about, what would I have to do to change this to represent a subtraction statement that ends up being an equality? What would it say? You got to relate 2 and 5 using some sort of a subtraction somewhere. What would it be? What is it? Where? 5 minus 3. Exactly. So this is the equivalent subtraction statement. It's what happens when kids are using the phrase fact families. You heard of fact families? We see it's a really common trend right now in mathematics with young kids, is this idea of fact families, is that if you know one of these, you should know the other. They're in the same fact family. So this is the similar statement for less than using subtraction. But what it asks me for on this problem is a whole definition, which means it's going to look a lot like what I've written down right here, but at the end right here, it's not going to have an addition statement. It's going to have a subtraction statement. So almost all of the phraseology can be exactly the same. We can say for any whole numbers, A and B, with A less than B. I mean, this is just verbatim, right? Written A less than B, just like that. There exists a whole number K such that what? This is the only part that changes. Right, A equals B minus K. And instead of adding the K to A, we subtract the K from B. Does that make sense? I believe you get to do a similar question where they ask you to do it for the phrase greater than, which is just the flip around of a less than, right? So it should feel very similar to this. I'd like to show you 4 whole number properties. Some of them you're familiar with in the sense that you use them quite frequently. Others, you use them and you don't even realize you're using them. So let's take a look. This first one is the one that you use without realizing you use all the time. And it's the one that causes people to trip up the most. It's called closure. The closure property says if A and B are whole numbers, then A plus B is a whole number. Okay? You use it all the time. If you add 2 whole numbers together, 7 plus 3, you don't find yourself looking for a fraction, right? Of course not. It doesn't all of a sudden become a decimal. No. Okay? But this property doesn't work for every set of numbers, right? If I found myself looking very specifically for what we traditionally think of as a fraction, it's actually possible to add a true fraction in fraction form, right? Not in reduced form, to another true fraction and end up with a whole number. You see what I'm saying? Like, that doesn't always work. This property. So this property is unique. It's unique because it's addition, and it's unique because it's whole numbers. So here's how I like to describe it. Imagine that you have in this room all of the whole numbers floating around in the air. They're all in the ceiling floating around. There's 1 over there, and 3 over here, and there's 7, and there's 10, and there's 12, and there's really big numbers too, like 62,598. Okay, they're all floating around in the room. And there's a door. If I can take 2 of these numbers out of the air that are floating around, i.e. whole numbers, and I can do this operation, addition, and when I add them together, the number that I get is still floating around inside the room. That's a closed system. It's closed because I didn't need to open the door to find any new numbers. I don't need anything extra. They're all already in the room. So it's closed. We'll talk more about closure later. Commutative. The commutative property is super awesome for kids because it means that all of their addition facts, they only have to learn half of them. You know what I'm saying? Right? Once you know that 3 plus 5 is 8, you really don't have to learn what 5 plus 3 is. You already know it. It's one of the best properties that there is for addition, and it happens again for multiplication. So the order of addition doesn't matter. Associative property is another really nice property. It says that I can reassociate values. Okay, so the order doesn't change. It's still A, B, C, A, B, C. But I can group together the A and the B, or I can group together the B and the C, or actually I could even like switch some numbers and group together A and C. That'd be using commutative and associative both. And I'm going to get the same answer no matter what. And the reason that that's helpful is because sometimes there are numbers that are easier to add together first. And usually it's because they add very nicely somewhere along the way to a 10. Adding to 10 is really nice. Adding to 14, not so nice. Associative property. Identity property says that there's a unique whole number 0, so that when you add it to something, it doesn't change things. In particular, you've used this property for quite some time when you add the same number like to both sides of an equation, right? When I add things together on both sides, it doesn't change a value. That's actually a portion of the identity property. So what we're going to do next is we're going to take a look at 4 examples, and we're going to identify the property that's going to be used in each example. 6 plus 8 is equal to 8 plus 6. What property is that illustrating? Yeah, that's the commutative property. People like to get creative with how they spell that. It is commutative. It's not communicative. It's not a community. You get weird ones on that one. How about the second one, B? It's the identity. And the reason is because there's a plus 0 on one side that subsequently does not change the 6 plus 3 that's on the right-hand side. So this is the, and we need to be very specific, this is the additive identity. The additive identity is the number 0. Multiplicative identity will be something different. How about the next one? Oh, we always want it to be associative because we see parentheses, but it isn't.
Oh,
It's actually commutative. So associative property actually changes the numbers that are inside the parentheses. But if you'll notice, the numbers inside the parentheses are the same numbers, 6 and 8. But the order of the 6 and the 8 switch. So when the order switches, that's the commutative property. But compare that to D. The numbers are actually different on this side, inside the parentheses on that one, right? This one says 5 and 3, but this one says 3 and 2. So this one is the associative property. All right, real quick, I just want to describe to you some basic addition and subtraction properties that you have seen. Actually, do I? Or do I want to save that for next time? I will save that for next time. This is a good place to stop. So we'll save that for next time. I'll post a video that I make sure includes the basic addition subtraction strategies and then the models for subtraction after that.